Good morning to Dr. Asri and Dr. Siti. My name is Khong Hao, and the PSM title to present is Discrete-time Neural Network Modeling of Industrial Air Compression System. First of all, let me go through the background of my research. The overall project research area is about three things: system identification, NARX-NN feedback modeling, and industrial air compression system. System identification (SI) is a modeling technique that uses input and/or output data to construct a relevant mathematical model. NARX-NN feedback model refers to a nonlinear autoregressive model with exogenous input with nonlinear neural network feedback function, while industrial air compression system is one of the most essential utility, ranked number 4 after electricity, natural gas, and water. In this project, the input is defined as the electricity supply rate and the output is defined as the manufacturing plant's compressed dry air usage rate. Next is about the project's objectives and scopes. There are three objectives in this research project: to perform system identification using neural networking technique, to apply the modeling method on industrial air compression system, and to analyze, validate the quality and performance of the NARX-NN model. Regarding the project scopes, there are four: applying the neural network modeling technique in SI problem, solve discrete-time single input, single output SISO system identification problem, utilize MATLAB's toolbox as simulation tool, and last, analyze the performance and dynamical behavior of mathematical model based on common performance indicators. The left picture is the flow chart of my methodology. The detailed description is all written in my report. Basically, this research is divided into 4 stages: data acquisition, data preprocessing, MATLAB comment, and simulation. The base training model selected is NARX-NN equation because it can fulfill the requirement of the system identification problem. The equation is shown in the right side of the slide. After the simulation stages, the best results obtained is shown as table below. The data division ratio for training to testing is about 90% to 10%, 10 number of neurons, and 2 number of delays. There are a total of 5 result validation parameters. We have performance mean square error plot, regression plot, response plot, error autocorrelation plot, and input error autocorrelation plot. The above figures show the performance plot of model training for 2 delays, 10 number of neurons, 90% to 10% data division ratio configuration. Because we are using Bayesian regularization as our training algorithm, both training and testing set mean square errors tends to reduce to the minimum value and does not display any overfitting symptoms. The left two figures shows the regression plot for both training and testing set. It can be noticed that most of the data points lay on a recursive line. However, a few data scatter around the plot due to the high mean square error between target output and predicted data. Thus, this situation would reduce the regression value, which means the accuracy of the model decreases too. Besides, the model configuration 2 delays 10 neurons, 90% to 10% data division ratio shows a decent result in the training set with a regression value R of 0.89206, which is the highest among the training. The testing set regression value R shows a slightly weaker result, 0.69441. The right figure is a regression plot for the overall results, combining all data from both training set and testing set. The regression value R for 363 data is 0.8641 and occurred to be the highest R value among all training. Here, the results indicates that this model configuration can train the most accurate results from the NARX model. This figure is the response plot generated from the neural net time series toolbox (NTS tool). The top plot shows the predicted output and the target data, while the bottom plot shows the relationship and error between both data. This figure is the error autocorrelation plot. This plot is used to validate the model's quality, and obviously the plot shows that the training result is way more reliable. All the error stays between the confidence limit except the one in zero lag, mean square error. At zero lag, the value is always maximum as it corresponds to the total energy of the input function, which is the similarity of the input function to itself. This figure is the input error cross-correlation plot. The correlation between the input data and error, difference of target and predicted value, mostly lay between the confidence limit, and it is a good indication for a good model. This result is in expectation as the normalization process is carried out. For the discussion, I would like to discuss about 3 questions throughout my research. The questions are, why increasing in training data ratio improves the model quality? Why high number of neurons do not perform well for this dataset? Why increasing number of delays results in performance declination? The short answer for above question 1 would be higher training ratio in a smaller size data usually refers to data size less than 1000, allows more data to be trained compared to a lower training ratio. At this instance, it results in a better performance. Next, usually high number of neurons is used when the data size is too big or the data is complex to solve. Unfortunately, data size of 363 neither is large nor complex. Therefore, its optimum number of neurons are found to be around 10 to 15. The last case is about increasing number of delays result in performance declination. The reason why this happened is because of the data collection method. This data were collected by average daily basis, and the usage demand of compressed dry air is different every day. In other words, the increasing of number of delays will execute the feedback comment with more and irrelevant continuous data, which will cause the model to train with less relational information and high errors. This is the comparison graph of predicted output and real-time industry target output. It can be noticed that the predicted output did not differ too much from the target output. Also, with the help of neural networks, some extreme data from target output due to random variables are not taken into concern during the prediction. In this project, a NARX neural network model identification method for the industrial air compression process is proposed. Before the simulation started, data acquisition and pre-processing were paid attention to because these 2 procedures are essential and will affect the model training quality. Besides, a predefined model architecture configuration must be identified ahead of simulation stages. The simulation model training is divided into 3 stages but executed continuously: data division test, number of neuron tests, and followed by number of delay tests. The outcome of model training using the Bayesian regularization algorithm had shown that the most suitable configuration is 2 number of delay, 10 number of neuron, 90% to 10% data division ratio for the data size of 363. This decision was made by comparing the performance, mean square error, and regression value. Also, the worst results generated through all the simulation stages occurred for 10 delays, 10 number of neuron, 90% to 10% data division ratio settings, where it is caused by the feedback of non-related future data. Here comes the end of my presentation, and special thanks to Professor Madhya, IR Dr. Fahmi. Thank you.